Welcome back, everybody, to our third and final piece of our three-part series, Solidity to Rust. As always, I'm your host, Julian Martinez, Senior Developer Advocate at SDF. And if you've been along with us throughout this journey, thank you so much. There are two previous videos, namely the Hello World video and the Data Types video. We'll leave resources in the description for you to check those out later on. But let's go ahead and kick this one off with a side-by-side code comparison. So today we're going to go through a bunch of cool stuff, namely inheritance, modifiers, authorization, event handling, error handling, all that and more throughout this tutorial, so stay tuned. We will be working with a incrementer contract that has access control functionality. The way we're going to achieve that is through modifiers and authorization. So starting off on the top of the list, we have a Solidity smart contract here, and let's go ahead and get into inheritance. So the way inheritance works in Solidity is like a family tree. As you can see here, we have our contract safe counter is addition contract, meaning we're inheriting all the functionality from addition contract, and we must implement the functions that live inside of the addition contract. So let's go ahead and head on over there. Oh, and by the way you import this is specified on line 3. We just reference the location of the contract itself, and we can import it that way. So let's go here. So here we have our addition contract. First things first, we have our interface. Now, interfaces are really cool because they allow you to implement different functionality throughout various smart contracts. So what does that really mean, right? So as long as an implementation follows these rules here and achieves the same end result, aka a uint256 in this case, then this function can be implemented within the smart contract. I like to think about it this way. Remember when you were a kid and your mom told you to get out of bed and clean your room because she wanted you to achieve a clean room, right? As long as I execute the tasks at hand with the rule set, aka getting out of bed and cleaning my room, and I achieve the end result, then it doesn't matter how I achieve the clean room, right? Did I actually get out of bed and fold my clothes, put them in the drawers? No, I kicked them under the bed and I got to the clean room, right? So that's exactly how implementing a interface is on a smart contract. It doesn't matter the methods I went about to achieve a clean room as long as the end result was the same. So let's break that down into the function here. As long as I'm following the rules by passing in a uint256A and a uint256B to achieve a uint256 sum, then I could still implement this function. So this is really great when it comes to cross-contract calls. An interface is the reason why you're able to implement a mint function into a contract that's not inside of a token and you're able to actually call the mint function on that token contract. For example, if I had this contract A, and the way I'm getting this sum is by adding A plus B, another contract, I can implement this function by adding B plus A. All that matters is that the end result is the same, and I can implement this function throughout any contract that inherits this. So let's go ahead and see the implementation in the safe counter. So we have the addition contract being imported, and we're using the function add here when we are getting the sum of the current count and adding that to the value. We'll go over how this is all stored in the mapping a little bit later, but first I want to go over how this looks on Soroban. So here's our incrementer contract, the safe counter, and we're going to import the crate addition contract. So let's go ahead and scroll up here. We're using use crate. We have the position of the contract here, addition contract. It's in the same library, and then we're importing the contract struct addition contract as well as the trait. Let's go ahead and see what that looks like. Instead of the interface keyword, we're using the trait keyword, and traits can be most comparable to interfaces in Solidity. So here, the exact same thing. This is our rule set, A and B, which are both U32s, and our end result is going to be a U32 as well. So here's the implementation of this function. We have A and B, and we're getting the end result. To get that, we're going to get the sum of A plus B. Again, if I had another contract that implemented this trait, I could do something like A plus A or B plus A. As long as I get a U32 at the end, I'm able to implement this function. And here's what it looks like in the function that we'll be calling. So we're going to define this count variable by getting the sum of the current count and adding the value that we'll be passing in for the function. And here you can see the struct we're using, the addition contract, and the function that lives inside of it. All right, so that covers inheritance. So let's go ahead and cover our next topic, modifiers and authorization. And we'll go ahead and dip in a little bit to errors and how they're handled on Solidity. So in Solidity, you can actually create these pre-execution rule sets called modifiers. Here we have a modifier that says only owner of counter. This means that only the owner of this counter mapping can modify the counter store and retrieve the data that lives inside of it. So we're going to be passing in an address as the argument for this modifier. And we're setting this, and the way we throw errors in Solidity is by setting requirements. So we have this require that the message sender, aka the person making the call to the function, is the user address. And if it's not, then we get this error message, caller is not the counter owner. This underscore signifies that the function will continue executing after this requirement is met. This is implemented in Solidity by placing it after the visibility annotation public. And as you can see here, we have an argument in our increment function that passes in the address user, and we'll be using that same argument to pass into our modifier. Now, how does this look like on Soroban? Well, we don't even have to add any other modifiers. We don't have to write any more code, nor do we have to import any contracts or crates for special access control. We can leverage native functionality right from the Soroban SDK with auth. So this line 78, specifies that the user address requires authentication before this function can execute, meaning the person who owns the secret key of this address must be the caller. So this is a really cool way to implement access control right from the native functionality of Soroban and really abstracts away a lot of the excess code that you may have to write in Solidity. Furthermore, this is going into the specifics of what this call actually does. So behind the scenes, it's actually doing require auth for args and passing in all the arguments and then signing with the private key of this with this user address, thus making it callable, thus making it executable. We'll get into how errors are handled a little bit more and what it looks like when this call is successful and what it looks like when this call fails a little bit more after this. So let's get into our next topic, error handling. All right, so for this demonstration, I'm going to go ahead and deploy some smart contracts here. Let's go over to the Solidity side. And we have this modifier that says only the caller of the counter can make this call. So let's go ahead and see what happens. So again, we're passing in the address, which is the address I'll be using to make the call. And then I'm going to go ahead and pass a value that's too high. We have the max value here set at 10, and we have our error handler here, the requirement that says the max value must be below or equal to 10, or else it's going to get this error message. So boom, we got this kicked back here. And let's go ahead and see what this looks like if we try to make a call from an address that is not the user. And boom, we got this error kicked back here. And then similarly, on the Soroban side, let's go ahead and make a call when the address is not the user. Get this error message that kicks back that an error was that. We get this error message signaling that the call failed. And because of the context of this smart contract, we know that this user did not pass the required authorization. I set this call up to contain the wrong public key on purpose. So this public key does not belong to this secret key. And we'll get into what it looks like when a call is successful later. But here is what a call looks like if a value is too high. We get this error message, max value exceeded. And that brings me to my next point of storage and how errors are stored, as well as how we're going to write and retrieve data from storage. So in Soroban, errors are stored in an enum. If you could look at line 46, our enum error, we're storing max value exceeded as the U32 0. We're also using the attribute macro contract error, which generates a conversion from a U32 into an awesome error message, and that's what you get here. I like the way that we're implementing errors on Soroban because it enhances the customizability of different errors. For example, if I wanted to set another one, I could maybe put something in there that says value too low, and this would map to error 1, and etc. I could do value must be above 5, value must be below 9, etc. And I would write different errors in this enum. Now, the way that we're going to be handling other storage here in this smart contract is through a key value store in another enum data key. So if you could see this data key here, counter, the data store counter requires that you pass in an address to access the storage slot. And the value that we're going to be writing to it is going to be a U32. So remember, the key of this counter is the address and the value is U32. And that's how we're mapping that. Let's go ahead and see how it looks on Solidity. Similarly, we're creating a mapping from an address to a uint256, and we're storing it in the counter object. So when we want to write data to this counter store here, we're simply going to overwrite the count that exists. So we're going to get the key, which is our user address, and then the value is going to be the sum of the current count and the value that we pass in for the argument. Let's go ahead and see what that looks like on Soroban. Here, we're defining the key as the address, as the store where the address lives. And then we're defining the count as the value of that store. We're simply going to redefine the count by getting the sum of the current count and the value. The way we're going to write that is by calling this set function here. So we have n.storage.persistent.set. We're going to be setting this to the key, which is the address, and then the count, which is the new value. We recently introduced state expiration, so now we have 3 different types of storage. First off, we have persistent, which is a high-cost type of storage that is recoverable post-expiration. This is best for long-term storage, such as things like balances. Next up, we have temporary storage. This is a cost-effective type of storage, and it's best for things like price oracles, signatures, and can be easily recreatable. The data also will persist after you restore the smart contract. And next, we have the shortest lifespan type of storage, instance. This is super cost-effective. It can only be up to 100 kilobytes, and it's best for shared contract state that that's not temporary, i.e. like admin accounts, contract metadata, and etc. So if you want to learn more about state expiration, you can go ahead and refer to the docs. I highly suggest you do so. It's a new implementation. And with this, we're going to be tackling the problem of state bloat. So now let's go ahead and move on to the next topic, events. Let's go ahead and head over to the Solidity side of things. Here on line 17, you can see where this event is written. We have this event increment executed, where we'll be passing in a user and a value. So here on line 35, where you see it being emitted, we should get an event that has the user address and the value that we pass in for the arguments. So let's go ahead and deploy the contract. Let's see what happens here. We can scroll down to the logs, and this will happen sometimes. So I'm going to go ahead and just redeploy this. And we'll make that call to the function increment. All right, I'm going to switch accounts. All right. And here in the logs, you could see we have the event, increment executed, and the data that is passed to the arguments, user, and value. Now let's go ahead and see what that looks like on the Soroban side. This is one of my favorite topics because we get to customize the event messages that are published to the blockchain. Here, we're leveraging the type or the struct env, and we're calling the events function and then the publish function. So we're also leveraging a macro symbol short, which is really cool for generating short strings. Our message is going to be increment. We're going to return the user address, the value passed in for the function, and lastly, the total overall count. So let's go ahead and see what this looks like. So Soroban CLI comes natively with a couple diagnostic events, but I'd like to bring your attention to this contract event here. And as you can see, we have our message increment, we have our address, and then we have the value. Lastly, we have the overall count. So this is how events are emitted in Soroban. You can do a lot of cool things that build off of events, like create subscription protocols, etc. I highly recommend that you look into the demos that we have around this. And lastly, I'm going to go ahead and get into calling a function from a contract that has logs enabled. So there's a special way to build smart contracts to include logs, which is going to give you an insight to what's happening behind the scenes after you make a call. So here's how this looks. So this is great if you're trying to debug a lot of the issues that you have in your smart contracts, as well as if you just want more insights to what's happening behind the scenes. We have this authorization call that we made. Furthermore, we have our contract event being emitted again, and then we have the entire footprint of the call that we made. Recently, I was faced with a blocker regarding a budget error. I couldn't figure it out. Eventually, I went ahead and optimized my smart contracts, made the same call, and it turns out I was actually hitting the CPU limit. So this is really handy when it comes to problems like this. As you can see here, we have a CPU limit of 40 million units. During this call, we're well under that, so around 1.6 million. And furthermore, the data is displayed to show you exactly where all your costs came from. So that concludes this video series. If you've been with us since the first two, really thank you from the bottom of my heart. And as always, if you're having trouble or you're getting blocked, you can leverage the resources available on the Soroban docs, or you can also reach out on Discord at Soroban-dev. Again, thank you for sticking with us. Until next time, take care.